Hi everyone, I'm Yuan Feng. I'm a PhD student from UC Merced. Today I will present our work, Barre Chord, Efficient Virtual Memory Translation for Multi-Chip Module GPUs. This is a collaboration work between UC Merced and Georgia Tech. Recent emerging applications like deep learning require tremendously large computer memory resources. Due to its superior performance, GPUs are the de facto standard accelerator for those applications. While the application keeps scaling up, it is hard for single die GPU to catch up the trend as the chip build decreases and the die become larger. Therefore, GPU vendors choose to produce multi-chip module GPUs or MCM GPUs. However, it is quite challenging to manage those ever large resources provided by MCM. Mechanisms like smart page migration and allocations are intensively studied, and such techniques heavily rely on virtual memory. But is the traditional virtual memory efficient enough for such novel MCM GPU architecture? Before jumping to our idea, let me first describe the MCM GPU based on the architecture that we target at. We consider a single GPU package that connected to whole CPU via PCIe. The GPU package connects multiple GPU chiplets. Here in the figure, there are 4 GPU chiplets. And each GPU chip is a fully functional GPU. It is equipped with L1, L2 caches, L1, L2 TLBs, and also each GPU chiplet has its own dedicated DRAM. Those GPU chips are connected via high bandwidth interconnections. Based on the baseline architecture, we now discuss what is the performance impact of virtual memory translation system in MCM GPU. Here in this figure, we demonstrate the performance with 8, 16, 32, an infinite number of page table walkers with 19 GPU applications. From experiments, we see almost a linear speedup every time we double the number of page table walkers, but it actually is saturated at 2x. This reveals that virtual memory translation is a bottleneck and require a fundamental revisit. Then one may ask, can existing conventional techniques solve the problem? We firstly evaluate the superpage solution by enabling 2 MB paging. Result shows that such coarse grain management will result in actual migration overhead and sometimes harm the performance. We then evaluate the TLB prefetching solution. Here in this figure, we present the page translation stride of adjacent request. Conventional prefetching rely on next page access or stable strided access. However, we find that if we change from a hypothetical shared L2 TLB to an MCM setting, the stride is much more diverse and unstable. Finally, there is recent work that targets multi-GPU cluster and propose to share TLB entry between GPUs. However, we find that under an MCM setting, the exact TLB sharing happens infrequently. In this figure, we show a hypothetical architecture that share L2 TLB. The result shows such hypothetical setting only bring marginal benefit. Motivated by the previous analysis, our goal is to provide an efficient virtual memory translation specifically designed for MCM GPUs. Our key insight is that memory allocation among different GPU chiplets can provide extra hints. Our idea is to provide those allocation hints and leverage them to coalescing address translation from different GPU chips. We firstly explore how the centralized IOMMU can leverage the structural page placement, we call it bar. We then explore how such hints can be shared and leveraged within the GPU, we call it full bar. Together we call it Barre Chord. We now discuss how pages are allocated in MCM GPU. On the left-hand side, it is a simple GPU program. The program contains 1 GPU kernel and 3 relevant data. Firstly, a kernel JIT compiler analysis is performed to analyze the access pattern within the GPU kernel. This is done by following existing works. Then, after capturing locality, a runtime GPU malloc driver call is evoked. By following the locality, data are allocated. Here, 12 pages are allocated at data 1, 4 pages are allocated to data 2, 3 pages are allocated to data 3. But since there's no rule, the page is placed at any possible location, and the page table walk is required for every single pages. We then introduce our key idea, coalescing group. The idea is to provide lightweight page allocation rule by mapping pages of the same data on the same physical location. Here, we intentionally enforce the same address to be allocated at the same physical location. For example, pages 0x1, 0x4, and 0x7, 0x8 are allocated at the same physical location 0x0075 at each GPU chip. And similarly, we process data 2 and data 3. We call those page groups that we enforce to look at the same position as coalescing group, and because they are at the same physical location, we can infer the other 3 addresses when we finish translating any one of them. Now let's see how such coalescing scheme can benefit the performance. In the baseline architecture, to translate all 19 pages, by assuming the L2TLB misses, you require all 19 page table walks. However, with Barre, when we finish one translation, we can check the page walk queue and find if there's any pending translation request that is in the same coalescing group and can be inferred without the actual page table walks. Overall, with Barre, we are able to finish the same translation request sequence with only 7 page table walks. Even though the coalescing group can potentially bring huge performance benefit, recording the coalescing metadata can bring noticeable overhead. Here we propose to encode the coalescing group metadata into unused bit in PTE. Let's take PTE 0x4 as an example. In the baseline S86 PTE, there are 11 bits remaining unused. So for the first 8 bits, we use them to store the validation information within the coalescing group. We call it coalescing bitmap. And for the rest 3 bits, we use them to store the rank information of each specific PTE. For example, for PTE 0x4, B11110000, it means that the first 4 GPU chips have valid PTE in the coalescing group. And 001 means the numerical value 1. It means it is the page 1 in the coalescing group. Then let's discuss how we decode the coalescing information from the PTE, how such information can be used. Here on the right-hand side, we propose a dedicated buffer to store the data objects called PEC buffer. The PEC buffer has 4 fields, the start and end VPN, and the interleaving granularity. The last field is GPU map that records how logical chiplet ID is mapped to physical chiplet ID. We then demonstrate an example that starting from a translated VPN 0x4 and translating VPN 0xa. We firstly check the starting and end VPN of each 2 PTEs and verify that they are in the same data. Then, by adding interleaving granularity, which is 2 times, we know that 0x4 and 0xa are in the same coalescing group. Since the multiplier integer is 2, we know that 0xa and 0x2 is 2 GPU away from 0x4. And since 0x4 is located at GPU 1, we know that 0xa is located at GPU 3. Finally, since 0x4 is a translated PTE, we know the PFN of it is 0xB075. By minusing the base address of GPU 1 and add the base address of GPU 3, we are able to finish the translation with simple calculation for VPN 0xa. Where Barre is able to call this page table walk that is located at the page walk queue and therefore boost the performance, there is still room to improve. Firstly, the GPU address are still translated at centralized IOMMU via slow PCIe. To solve this, we propose intra-GPU translation to keep the coalescing and translation within the GPU package. Secondly, coalescing group size is limited by the number of shared GPU chips. This limits the potential performance benefits. Our idea is to propose continuity-aware coalescing group expansion. Thirdly, the coalescing oblivious page walk scheduling limits the opportunity of coalescing PFNs. To address this, we propose coalescing-aware page table walk scheduling. Based on Barre Chord enhanced with those 3 optimizations are called FOBAR or FBAR. In this talk, I will cover first 2 optimizations. Please refer our paper for the third one. We first introduce the first optimization, intra-GPU translation. The idea is to share the coalescing information among the GPU chiplets. Here, we integrate 2 cuckoo filters per GPU chip. One is called remote coalescing filter that is used to tell which remote GPU chiplets contain the coalescing group that has requested translation. The other called local coalescing filter, which is used to predict whether local GPU contains the coalescing information that remote GPU asks for to avoid exhaustive search. Operational-wise, we firstly check RCF to get the potential remote GPU chip that contains the requests. Then it will send the request to the remote GPU. Then remote GPU will query its LCF and check local L2TLB. If all of them return a hit, our translation results will be returned to the original requested GPU chip without a page table walk. In the baseline Barre, we are able to coalesce multiple GPU translation requests in the same coalescing group, but only at IOMMU. With the proposed intra-GPU translation scheme, we are able to share the coalescing information among different GPU chips and share it within the GPU package and further boost the performance. The second limitation of Barre Chord is the coalescing group size is limited by the number of GPU. Our solution is called contiguity-aware coalescing group expansion. Our key idea is to opportunistically expanding the coalescing group when memory allocation contiguity is observed. Here, suppose that we are still trying to allocate 12 pages for data objects. But while we're constructing coalescing group, the driver finds that there is contiguity available to explore. Then F-bar is able to expand those two contiguous coalescing group into one coalescing group and enlarge the coalescing range. Here, to support the expanded coalescing group, we also further modify the Barre Chord PDE to encode the merging information. Performance-wise, without contiguity-aware coalescing expansion, the coalescing group size is limited by the number of chips. And in the example, one page table walk can only cover up to 4 PTEs. With contiguity-aware F-bar, we merge coalescing groups. Therefore, the X5, the X2, the XB, the X8 can be translated alongside the XA. The performance can be further boosted with larger coalescing group because one page table walk can cover up to 8 PTEs. For evaluation, we use a cipher level simulator MGPU sim to conduct the experiments. We model a G-Sens 3 like AMD GPU. Each GPU package contains 4 GPU chiplets. GPU chiplets are connected via 768 Gbps interconnections. We model CPU-GPU connections similar to PCIe Gen 4. We model LMMU to have 16 page table walkers in the baseline, and it is equipped with a 48 entry page walk queue in the baseline as well. For overall performance, we compare against baseline and two state-of-the-art work. On average, Barre Chord is able to achieve 1.36 speedup over the SOTA work on average. If we opportunistically merge 4 coalescing groups, Barre Chord can provide 1.53 more speedup. Such noticeable performance benefit is because Barre Chord is able to fundamentally remove expensive page table walks. In this figure, we present the performance benefit under different number of GPU chiplets. Overall, when there are more GPU chips integrated in the system, Barre Chord is able to construct a larger coalescing group, and the performance benefit becomes even larger. We have more detailed evaluation like breakdowns, GMMUs, superpages, and much more. Please check our paper for more detail. Thank you very much.